Well, good morning. This is going to be chapter 18, day 1, and this whole chapter is about confidence intervals for proportions. All right, so the overall chapter objective is to explore confidence intervals and how they apply to the real world. All right, so to start this conversation, we're going to quickly review something that we just recently talked about. Okay, so we learned in the previous chapter that the sampling distribution proportion has a standard deviation. So if you recall, the mean of the sampling distribution is p. The standard deviation of p hat is the square root of pq over n. Now, in order to do this, this is a quick note, we need to know p. And p, if you recall, is the population proportion. Now, it turns out that we often don't know p, okay? And there is our issue. Okay, so what do we do? Okay, we would love to use the normal model to approximate the sampling distribution for the proportions. In order to use the normal model, we need a mean. So we know that the mean of all p hats will equal p eventually. And then the standard deviation will look like the square root of pq over n. But we really don't know what that value of p is. So what do we do? Okay. So when we don't know p, we're stuck, right? Well, it turns out we're not stuck. So we will use sample statistics to estimate population parameters. So what that means is, okay, the best estimate of what our population p is, okay, will be our sample statistic p hat. So we're going to estimate what p is. So p is going to be approximately what our p hat is, okay? And the same thing happens for mu. So the best estimate of our population mean, mu, will be x bar. So we can say mu will be approximately x bar, okay? Now, when we use an estimate to approximate our standard deviation, we get a little bit of an error, and then we're going to call that the standard error as opposed to the standard deviation. So we have a new formula. This actually looks to be exactly like the standard deviation. So instead of using p, we're now going to use p hat and q hat in this formula, and we're going to call it the standard error. So it's like the standard deviation for p hat, except we use p hat instead of, okay? So this introduces error, okay? So what do? Recall that the sampling distribution model p hat is centered at p with the standard deviation of the square root of pq over n. Since we don't know p, we can't find that true standard deviation of sampling distribution, so we will find a standard error. Okay. Now, the great news is we can actually get a really good estimate of what p truly is. And by doing that, we will talk about a confidence interval. So a confidence interval lets us guess the interval that contains the true population proportion p, okay? And it turns out all we really need is our p hat, our population, our sample proportion, and we just need to calculate a standard error and go out 1 unit of standard error for 68% of my data, go out 2 units of standard error for 95% of my data, and then go out 3 units of standard error for 99% of my data. And what that does is it will capture values that I believe my true p will be in, okay? So consider the 95% level. If we reach out 2 standard errors, we are 95% sure that the true p will be in that interval. In other words, if I reach out two standard errors in either direction of p hat, we can be 95% confident that this interval contains the true proportion. This is called the 95% confidence interval. All right, so here's how we actually build it. We find a p hat, we will add 2 units of standard error and subtract 2 units of standard error, and these gives us values, okay? This contains the confidence interval. And what we're saying is we think that true p is somewhere inside of that confidence interval. Now, we don't know the exact value of p, but all we really know is that that true value is somewhere inside of that. Now, with statistics, sometimes we're right and sometimes we're wrong. So there are possibilities that that true p was actually on the outside of that confidence interval, right? But with statistics, I can be confident with a certain degree of confidence that I did actually capture my true p. Okay, let's take a look at this first example. So a medical researcher estimates that the percentage of children exposed to lead-based paint, adding that he believes that the estimate has a margin of error of about 3%. Explain what this margin of error means. Okay, so here is how I would explain what this researcher has come up with. All right, so let me just go ahead and fix this a little bit. There we go. Okay. Just trying to get my text box and the rest of my box here. All right, so I might write the following, okay? He believes the true percentage, that's our p, of children who are exposed to lead-based paint is within 3% of his estimate, with some degree of confidence. Now, this is not stated what confidence we have, but we might think it was 95%. That's a typical confidence level. Okay? So another way to think of that is the researcher has an estimate p hat, and he's going to add and subtract a certain margin. Okay, and that margin is going to be 3%. Okay, this is what's called the margin of error, and we'll talk more about how that formula is set up a little bit later. All right, let's take a look at example 2. So let's consider each situation described. We're going to identify the population and the sample, explain what p and p hat represent, and tell whether the methods of this chapter can be used to create a confidence interval. So let's take a look at A. So A says a consumer group hoping to assess customer experiences with auto dealers surveys 167 people who recently bought new cars. 3% of them expressed dissatisfaction with the salespeople. All right. So in part A, and I'll try to write this over here. So the population is going to be all customers who recently bought new cars. Okay. The sample is going to be 167 people surveyed. About their experience. Okay. And then p hat is going to be my 3%. Okay. Now, going through these, all of the following we have to kind of check. So do I have independence? All right. Well, in this condition, I guess it's safe to assume one person's being independent of another. But in reality, that's okay. We have a survey, so we can only assume that it was probably done randomly. But we do know that we have less than 10% of the population. So we're good to go there. Let's check our NP and Q condition. So if I do N times P, okay, and then I don't really have a P, so I'm going to approximate that with P hat. So our N was 167, and I'm going to multiply that by 0.03. And when I do that, I get 5. When I do N times Q hat, I get 167 times 0.97, and I get 162. So this condition here is not satisfied. So I cannot use the methods of this chapter. Okay. All right, let's try part B here. So what percentage of college students have cell phones? 2,883 students were asked as they entered the football stadium, and 243 said they had phones with them. So our population is going to be all college students. Okay. Our sample is going to be the 2,883 students surveyed. Okay, our P hat is going to be 243 divided by 2,883, which is approximately 8.4%. All right, let's check independence. All right, was this random? This was not a random survey. Okay, they were asked as they entered a football stadium. Plus, we only talked to people at a football stadium, so it's not really representative. It is 10%. 2,883 is less than 10% of all college students, so that's okay. And then NP and NP hat and NQ hat will both be greater than or equal to 10. So yeah, we can, but the sample is not representative of all college students. All right. Example 2. So we're going to consider each situation described still, same thing. So in part C, okay, we have 200 potato plants in the field in Maine, and then we randomly check them, and 7 show signs of blight. How severe is this blight? All right, so in C, the population is going to be, all right, potato plants in the US. All right, our sample is the 240 in Maine. Our P hat is going to be 7 out of 240. Okay, independence. Okay, so let's check that. Do I have a random sample? Yes. 10%? Yes. Now, independence. This is a big one. This is not independent. If one potato has blight, blight is an infectious thing. So it's going to cause other potatoes to get blight a lot faster. So these are not independent, really. Okay? In addition, if I check N times P hat, that's going to give me 240 times my P hat, which is going to give me 7. That's less than 10. So we can't use the methods of this chapter. All right, well, let's check out part D. All right, so 12 of 309 employees of a small company suffered an injury on the job last year. What can a company expect in future years? All right, so my population is going to be all employees at the company. My sample is the 12 excuse me, the 309 surveys we talked to, my p hat is going to be 12 over 309. Okay. Let's see, independence. Okay, it's reasonable to assume one employee is independent of another. Okay. Do we have a random sample? It's not random. Okay, it is reasonable to assume, let's just write this, reasonable to assume independence. We don't have a random sample. Okay. But this is probably representative. Okay. It is less than 10% of all employees, I would assume. I don't know. Okay. The problem is this is a small company. Okay. N times p hat is going to give me 12. And then n times q hat is going to need to give me 297. And then both are greater than or equal to 10. So I could. All right, chapter 3, example 3, excuse me. So in January 2009, 2 students made worldwide headlines by spinning a Belgian euro 250 times and getting 140 heads. That's 56%. So that makes a 90% confidence interval, which is 51% to 61%. What does this mean? And are these conclusions correct? All right, so let's kind of show you what they're doing on each one of these here. So to construct a confidence interval, we basically take our p hat plus or minus some value, which I'm going to call something later, times our standard error, p hat, q hat over n. Okay, so this number here that we're going to use, this factor, is going to be found by using our confidence level. Okay, so in this problem, what they did, they took the 0.56, they added or subtracted some number, and then times the standard error, 0.56 times 0.44 divided by 250. And that is how they got the interval between 0.51 and 0.61. And what that says is we think the true p lies somewhere inside of this interval. Okay, we think this. We don't know where it is, but we think it's there. All right, so part A. Does this mean that between 51% and 61% of all euros are unfair? No, not correct. This is not correct because this statement implies certainty. There is no level of confidence with this statement. This says all euros are unfair. No, we just know that we're 90% confident the true p will be, the true proportion of heads that will come up will be between 51 and 61%. All right, B. We are 90% sure that in this experiment, this euro landed heads on between 51% and 61% of the spins. This is, again, not correct because we know 56% of the spins happened. There is no need to make a confidence interval for a proportion. Confidence intervals guess the true p, not p hat. We know what p hat is. All right, C, we are 90% sure that the spun euros will land of heads will be between 51% and 61% of the time. That's correct. All right, D, if you spin a euro many times, you can be 90% sure of getting between 51% and 61% of heads. Okay, this is not correct. Okay, because this is about spins, not heads. Okay. E, 90% of all spun euros will land between heads between 51% and 61%. Okay. E, this is not correct as well. Okay, because the interval should be about the proportion of heads, not the percentage of euros. Okay, so this always tells us what we think the true p will be. Remember, the p in this case is the proportion of heads. Okay. All right, and our last example for today's video. So several factors are involved in the creation of a confidence interval. Among them are the sample size, the level of confidence, and the margin of error. So which statements are true? For a given sample size, reducing the margin of error will mean a lower confidence. So A is true. Okay. The smaller the margin of error is, the less confident we have in our ability to for our interval to catch the population proportion. B, for a certain confidence level, you can get a smaller margin of error by selecting a bigger sample. That is true. Okay. Larger samples are less variable, which translates to a smaller margin of error. We can be more precise at the same level of confidence. C, for a fixed margin of error, smaller samples will mean a lower confidence. That's also true. So smaller samples are more variable, leading us to be less confident in our ability for our interval to catch the true population proportion. And D, for a given confidence level, a sample 9 times as large will make a margin of error 1/3 as big. This is true. The margin of error decreases as the square root of the sample size increases. So in reality, remember the margin of error is built by this. It's going to be p hat plus or minus the margin of error. And then p hat plus or minus, and that margin of error is taken by a number times my standard error, p hat q hat over n. So for this last one, if you plugged in 9, you're going to get the square root of 1/9, which is 1/3. So that's why you get that. Okay. And that is the end of part 1.